Okay. So last time we were looking at gravitational redshift, and we studied gravitational redshift in the Schwarzschild geometry. And uh, what we said was that uh, at any ordinary point in the Schwarzschild geometry, you should be able to write down the metric in the Minkowski form, and therefore the laws of special relativity should be applicable. This is just a statement of equivalence principle. So therefore, at any at any point in the Schwarzschild geometry, uh, maybe I should say any ordinary point in the Schwarzschild geometry, if you want to study, say, hydrogen atom spectrum, then it would look the same. Uh, by that I mean that the ground state energy would be minus 13.6 electron volt, and the spectrum would depend on the principal quantum number, as uh, it would be proportional to 1 over n squared, where n is the principal quantum number. Okay, so what is the meaning of gravitational redshift then? The meaning of gravitational redshift is that the hydrogen atom spectrum determined at one point in the Schwarzschild geometry, uh, how is it? How is that spectrum perceived at some other point in the Schwarzschild geometry? And the question is this is the energy spectrum going to change? Is it going to be higher energy, lower energy? Uh, and if it is going to be of higher energy or lower energy, then what? How do we actually determine this? Okay, so the point that we saw last time was that that if you want to do a local experiment, you will never be able to figure out this difference. Only way you would be able to figure out the difference is that you look at a transition at one point and detect the transition at another point. So that is why we did this study, that we keep the hydrogen atom at R equals RA, and we make the measurement at R equals RB, where R is a radial distance in the Schwarzschild geometry, and we choose RB to be much larger than RA. Okay, and then we find that the frequencies measured at RB are less than the frequency measured uh, the frequency emitted at RA. Frequency emitted at RA for our example was very specific. We looked at the Balmer series from n equals 3 to n equals 2 transition. Okay, so that corresponds to one of the visible light, visible range of lights, and we should be able to detect this one by bare eyes. On the other hand, when we measure it at R equals RB, uh, in fact, this light is not even visible. Okay, so this light n equals 3 to 2 is actually in the range of longest wavelength within the visible spectrum, namely red lines. Okay, but by the time it reaches RB, the frequency goes down, and it is actually something in infrared or even uh, longer wavelengths like microwave and so on. Okay, depending upon how far is RB from RA. Okay, so now as we saw that physically what is happening is that if RA is smaller than RB, then the gravitational energy available at R equals RA is larger than the gravitational energy available at R equals RB, and as a result, you would have you would think that the energy available at R equals RA is much larger. Okay. On the other hand, the observer sitting at R equals RB is going to conclude it's exactly opposite. The observer sitting at R equals RB is going to conclude that the frequencies at R equals RA are redshifted. Okay, fine. So And the reason why this is being done is because the observer sitting at R equals RB is comparing the hydrogen atom spectrum in his or her local frame with the hydrogen atom spectrum in the local frame of the observer sitting at R equals RA. Okay, so, and as we said last time, that the reason why this redshifting occurs is that when the light goes out from R equals RA to R equals RB, it has to overcome the gravitational potential, and a lot of energy is spent into overcoming the gravitational potential, and therefore effective wavelength of the light measured at R equals RB is larger. Fine. Okay. So,
Hello.
excuse me. Yes.
Yeah, in the non-relativistic case, we said that the gravitational energy means the gravitational potential energy. But what is the analog of the gravitational energy here?
Sorry, I didn't understand the question.
In the non-relativistic case, we used to say that there is a phi minus gm over r, that is the gravitational energy.
Yes.
And here, what is that?
Well, here,
I mean,
here
is
it is the effect of curvature, right? So it's the same interpretation. Locally, if you try to interpret, it is still a gravitational potential, right? The G00 factor, okay, right?
okay. That can only be said as at a limit. I mean,
At a limit means, no, you don't have to take a non-relativistic limit. You could still kind of figure out that you will have to spend extra energy simply because your G00 is not say -1, right?
okay.
Okay, so all your energies are getting, you know, uh, redshifted simply because your time is clicking differently, right? Is that okay?
Yeah, fine.
Yeah. Okay. So the other thing that we looked at last time was the notion of distances between concentric spheres. Okay, and we said that, like, in the flat space, distances between concentric uh, spheres was just the difference between the radii. So if there's a sphere of radius r1 and sphere of radius r2, which are concentric, that means their center is same. Then the distance between the points on these spheres, the shortest distance would be just r1 minus r2 modulus of that. Okay. On the other hand, in the Schwarzschild geometry, that's not what happens, and that is simply because the metric is written as d rho uh, squared upon 1 minus 2 gm by rho. That is the kind of factor we have. So therefore, or if I write d rho, it should be a square root, as was pointed out last time. Okay. So to measure the distance between two radii, rho and rho plus d rho, what you really need to do is to actually do this kind of integration. Okay. So when you do this integration, you find that the distance is always larger than rho 1 minus rho 2. Okay. And there is a factor uh, which is gm times log of rho 1 by rho 2. We are assuming that rho 1 is larger than rho 2. So therefore, this number is always positive. Okay. So the best way to draw the geometry is to actually draw it in this particular fashion. Instead of drawing concentric spheres in this fashion, you draw a sphere at radius rho 1 here and sphere of radius rho 2 down here, and you measure the distance in this particular fashion. So this distance in flat space would be clearly smaller than this distance that we are measuring in the Schwarzschild geometry. Okay. Then we carried out some small manipulation to just make this effect look a little more pronounced by changing the coordinate system, replacing rho by new coordinate r, and manipulating the metric to write down the proper time d tau squared in this particular fashion. Fine. So now if you try to look at the distances between concentric sphere, you can forget about the time. You can just choose dt equals 0, and then you'll find that the concentric spheres are mm, not separated by r1 minus r2, but there is a factor 1 plus gm over 2r to the fourth sitting around, okay, which makes the thing look much more pronounced because of the fourth power. But if you really go to very large radii, very large values of r, then this fourth power is of no consequence, simply because 1 plus gm upon r, with r very large, is roughly equal to 1. Which just tells you that Schwarzschild geometry is asymptotically flat geometry. Okay. Okay. So rest all is basically just the statement that you are setting dt equals 0 and d omega equals 0, just to try to understand what is the distance. Okay. So let's get back to the Schwarzschild metric again. And so this is Schwarzschild metric. And what we want to understand is that that we do see that rho equals 2gm is some special point, okay, and we want to understand as to how special is that point with respect to different kinds of observation that we would want to do. Okay, so first thing is that, like, of course, gtt goes to 0 and g rho goes to infinity at rho is equal to 2gm. Okay, but the other point which we had mentioned earlier, and that was that when rho is less than 2gm, then GTT is is positive. Okay, because 1 minus 2gm by rho is negative, and then this minus sign gets soaked up. Whereas 1 minus 2gm by rho becomes negative here, and therefore g rho becomes negative. Okay, so so therefore uh, p becomes space-like coordinates and rho becomes time-like coordinate. Okay, fine. So what you would call constant time surfaces would be the surfaces which would be constant spatial surfaces for rho less than 2gm. Okay, now let's try to understand this a little better. So let's try to study light cones. Okay, so to study light cones, what we will do is we will write down uh, the proper time, but set that equal to 0, simply because we are looking at light cones. Okay, and then we will just ignore the angular part of the metric. Okay, because typically to study light cones, you don't really look at the angular part of the story. Okay, so that leaves us with the equation which is minus 1 minus 2gm over rho dt squared plus d rho squared upon 1 minus 2gm by rho equals 0. Okay, so you can kind of use that equation to find that dt by d rho is equal to plus or minus 1 over 1 plus 1 over 1 minus 2gm by rho. Okay, but dt by d rho should be really 1 for the light cone, right? So therefore you would kind of say that if you are in the flat space geometry, you would have said dt by d rho equals 1, and you would say that that defines the light cone for us. Okay, and that is the quantity which makes sense when rho goes to infinity. Okay, because precisely in that limit that you will get dt by d rho equal to plus or minus 1. Okay, but that's not what happens for arbitrary finite values of rho. For example, rho equals 2gm, which is the extreme limit. Okay, dt by d rho is actually infinity. Okay, so if you want to draw light cones, based on the what is the value of dt by d rho, you will find the light cones would look something like this. Okay, that far, very far away for large rho, the light cone is actually 45-degree cone. But as you look at finite values of rho, this angle starts shrinking. Okay, and it keeps shrinking until you hit the point rho is equal to 2 gm, at which the uh, the two light cones actually just merge, okay, and into a single light line. Okay, and uh, you know that this line would have had a positive slope and this line would have a negative slope, but the slope is kind of growing as you go for smaller and smaller values. This line goes to positive infinity slope and this line essentially goes to negative infinity slope, but both of them are essentially same lines. Uh, It also means that rho equals 2 gm is a surface which is null, simply because the light cone is actually tangent to this surface. Okay, so therefore, besides kind of finding that the metric component seems to be diverging at rho is equal to 2 gm, we also find that rho is equal to 2 gm is a surface which is null in the Schwarzschild geometry. Is there a question? Okay, so another thing that we would conclude is something which is written out here, that the light rays which approach rho equals 2 gm would never seem to reach there. Okay, and that is the reason. The reason for that is the following: that as the light, as the asymptotic observer sees the light kind of falling in, okay, it seems to be taking larger and larger amount of time to reach from one point to another point as rho starts going down. Okay, and by the time it reaches rho is equal to 2 gm, okay, it in terms of the clock of the asymptotic observer, infinite amount of time would have passed. Okay. Fine.
Huh?
Now, of course, yes.
Can it be a result of the fact that we have ignored the theta phi terms here?
No, no, no. It has nothing to do with theta phi at all, like, in fact. Okay.
Well, maybe if we allowed the theta phi and phi to be, I mean, d theta and d phi to be non-zero, then maybe that this dr may not be zero. I mean, that might be possible, right?
What may not be zero?
I mean, yeah, here we have just taken the rho and t part. We have ignored
Yes.
that omega part. If we had
Yes.
allowed omega, then might be d rho should, I mean, could have had some value.
No, no, no. What we are doing is we are just looking at radially infalling light. Like, imagine, like, you send a light directly in the direction of the massive body. Okay. In that case, this angular value would never change, right?
Okay, but I'm saying that if we allow this omega to change, then will it be again true that this will take infinite time?
Yeah, yeah. It would still take infinite time
How?
because uh, as rho starts going closer to 2 gm, the GTT becomes smaller and smaller value, right?
Oh, from
One can also see this using this equation dt by d rho if one simply integrates this.
no.
Exactly.
Here
Yeah.
we ignored that omega part.
So even if we ignore the omega part.
It doesn't matter actually. Omega is not playing any role.
Yeah, okay, got it. From the G not term it happens.
Yeah, it is a G naught naught term which is like ticking very slowly. As a result, as you go closer and closer, the time itself is kind of uh, ticking.
Logarithmically diverges, right?
Yeah, logarithmically divergent. Exactly, and we will do that in a moment actually.
Yeah.
Now the thing is that this closure of the light cone is something that we are not very kind of used to. In special relativity, for example, light cones are always 45-degree lines. Okay, so therefore, geometry of this kind is a little bit kind of difficult to understand. Okay, so what one can do is that instead of working with geometry of this kind, we can work with a geometry in which light cones are always at 45 degrees. Okay. Now that makes life a little simpler because we understand light cones at 45 degrees. Okay. So what we'll do is that we will kind of write down new coordinates in which we will ensure that these light cones will always make 45-degree angles with respect to the horizontal. Okay. Now, as I was trying to say was that mm, that this perception of light cone shrinking is a perception from the point of view of an asymptotic observer. Okay. And therefore, the asymptotic observer would say that the light would never reach rho equals 2 gm because at rho equals 2 gm, you can clearly see that the light would be just stationary. It wouldn't move, change the value of rho. In fact, even little further away from rho equals 2 gm, the light cone is really narrow, and therefore the light would not travel much uh, from the asymptotic observer's point of view um, for reasonable amount of time, because time is a vertical direction, space is a horizontal direction, right? So, and the light cone, if it is making very large angle, then for large amount of time, the distance travel in rho direction is very small. Okay, that is how the observer is kind of perceiving it. Okay, and therefore the observer at infinity would say that the light ray will never reach rho equals 2 gm. Okay, now you really don't need the observer at infinity. Observer sitting here also would never see the um, light reaching rho equals 2 gm in finite time. Okay. So therefore, observer will never, because of this illusion, the observer will never find out that the object that he or she has sent in, or the light uh, shown on this point mass, would ever reach this point itself. Point mass is like way inside at rho is equal to 0. Okay, and it will just never see that. Okay. Fine. Now, we would like to understand as to why is it that it is happening this way. Okay. Now, to 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 understand this, what we need to do is to have another observer who is falling in along the radial null geodesic. Okay. So we have this light-like geodesic which is falling in. Okay, towards the point mass. Okay. And suppose an observer is following that geodesic, is sending the signal back to the observer who is far away, okay, at a regular interval. The regular interval that the infalling observer would be counting, okay, would be the coordinate time that the infalling observer would be using to um, measure time in his own local clock. And the reason why it is coordinate time is simply because in the infalling observer's frame, you can always go to Minkowski space. And in the Minkowski space, your coordinate time is multiplied by a factor. I mean, for us, in our case, it will be multiplied by a factor of -1. Okay, with respect to proper time. Okay, so therefore, the infalling observer would be thinking that the message is being sent to the asymptotic observer at regular interval, but from the asymptotic observer's point of view, the metric is not just flat, but is 1 minus 2 gm by rho uh, sitting in front of dt squared, and therefore the asymptotic observer will see the signals reaching uh, progressively slower as the infalling observer goes closer and closer towards the point mass at rho equals 0. Okay. Now, this fact is essentially related to the fact that the distances between two concentric spheres with respect to the asymptotic observers is always greater than the rho, the difference between two radii. So if radii are rho 1 and rho 2, then the distance is always larger than mod of rho 1 minus rho 2. Okay, fine. So we have a double effect. One effect is because these spheres are kind of at larger distances than what you would have thought, and the time intervals uh, are getting smaller simply because G00 or GTT is getting smaller as rho becomes smaller. Okay, fine. So, so these two effects kind of combine together to give the effect to the asymptotic observer that the that the infalling observer following the light-like geodesic, that means essentially that observer is light itself, okay, will never reach rho is equal to 2g. Okay, fine. Now, all these arguments are, of course, uh, making complete sense. In reality, however, if you try to see what happens to the infalling observer, the infalling observer would actually cross rho equals to gm infinite time. Okay, so and there is no contradiction with this uh, contradiction between this statement and the previous statement that the infalling observer would take infinite time to reach rho equals to gm with respect to an observer who is sitting at very large value of rho, versus in the frame of the infalling observer, uh, he or she would cross rho equals to gm infinite time. Okay. Right. Now, this discrepancy is purely because of the choice of coordinate system, okay, and nothing to do with the real situation. Okay. So, as I was trying to explain, that it is taking larger and larger time for the signal to reach large value of rho, say rho equals infinity, and that is why the observer at infinity is concluding that the infalling observer is not reaching rho equals to gm. As far as infalling observer is concerned, the message is being sent at regular interval, and the fellow is seem to be falling in at at a kind of usual pace and crossing the different values, smaller and smaller values of rho at regular intervals. Okay, and therefore would cross rho equals to gm infinite time. Okay, so what we should really do is to look at quantities which are really coordinate independent, and not based on what is asymptotic observer is kind of observing, or what the infalling observer is observing, or what is the observation of a specific observer who is accelerated with respect to this geometry and so on. Okay, and the coordinate independent quantity is typically proper time. Okay, so we could ask a question that is the infalling observer reaching rho equals to gm in finite proper time? Okay, that makes much more sense as against whether the asymptotic observer sees the infalling observer crossing rho equals to gm infinite time or not. Okay, fine. So to do that also, it is a good idea to have our light cone fixed to be at 45 degrees. Okay, so what we will do is we will uh, change the coordinates. Okay, and to change these coordinates, all we will do is to take this equation dt by d rho is equal to plus or minus 1 over 1 minus 2 gm by rho and integrate it. Okay, and this is eminently possible to do the integration. Okay, and the integration gives you t is equal to rho plus 2 gm times log of rho upon 2 gm minus 1. Okay, to put it a little differently, if you differentiate this equation, you will get this statement. Okay, so what we'll do is that if you want to have light cones at 45 degree, then with respect to light cone, you would want to have dt is equal to this quantity. So suppose we define this as a new coordinate, let's call it rho star. Then t is equal to rho star tells you that in the t rho star coordinate system, the light cones are always at 45 degree. Okay, now rho star itself is a complicated function of rho. So in the t and rho coordinate system, light cone could be shrinking, but t rho star coordinate system light cones are not shrinking. Fine. So once you have rho star defined this way, you can define d rho star, and which is d rho plus 2gm upon derivative of log, which is 1 over rho minus 2gm minus 1 times 1 over 2gm times d rho. Okay. So you can simplify this quantity and you find that d rho star is equal to just 1 over 1 minus 2gm by rho times d rho. Okay. And now you find that T is equal to plus or minus rho star up to some constant are basically radial null geodesics. Okay.
So this coordinate might not work when rho is less than 2 gm, right? Because
Yeah,
log.
no, it will not work in fact. Okay. So this coordinate rho star is defined only for rho greater than 2gm.
Okay.
These are equal to at best. Okay. And that is the way we will actually explain as to why the asymptotic observer never sees the infalling observer reach rho equals 2gm. Okay. So let's just go a few steps and we'll see what happens. Okay. Okay, so this equation in the bracket in written in terms of rho star coordinate system is basically t is equal to rho star. Okay, because rho star is precisely the right hand side of this equation. Okay, so we could have radial null geodesics having values t equals plus or minus rho star up to some constant. Okay, so lines which are t minus rho star is equal to constant are basically outgoing null geodesics, because as t grows, rho star also grows, so that t minus rho star is equal to constant. Okay, so that is, since rho star is growing, that means it's outgoing trajectory. On the other hand, if t plus rho star is constant, then it's an ingoing null geodesic, because as t goes up, has to go down, rho star has to go down, so that t plus rho star is constant. Okay. Now notice one thing, that when rho is equal to 2gm, okay, then rho star is equal to minus infinity. Because although this quantity is 2gm, this quantity is log of 1 minus 1, which is log of 0, is minus infinity. So the range of rho from 2gm to infinity gets mapped to range of rho star from minus infinity to plus infinity. Okay. So therefore, only the region outside rho equals 2gm is the domain in which rho star is defined. Okay. And that is the reason why rho star is typically called the tortoise coordinate. Okay. Uh, Part of the reason why it is called tortoise coordinate goes back to something called Xenos Paradox. And the Xenos Paradox basically says that if you have a race between a tortoise and Achilles, who are supposed to be one of the fastest running mythical Greek person, uh, the Zeno's kind of argument was that if it had given some head start to tortoise, okay, then Achilles will never be able to catch up with tortoise. I suppose you know this particular paradox. Do you?
It's about like convergence of infinite series.
Yes, yes. These are related to convergence of infinite series, which Greeks didn't know for quite some time. You see. Yeah. So, but uh, but in the gravitational setup also, you could kind of come up with Zeno's paradox of this kind, that if you have an accelerating body, then if it is if a if a body is accelerating at constant acceleration for quite some time, you can show that light will not be able to catch up with it, because light at is at constant velocity, whereas this object is at constant acceleration. Okay, and so therefore, according to this setup, you will find that the constant accelerating body would leave a black hole behind. The reason why it's called black hole is because light sent from behind uh, will never be able to catch up, and therefore there is no light reaching the accelerating body, and therefore the body uh, taking image in the backward direction would say that there is no light coming in that direction, and therefore it's a black hole. Okay. So tortoise coordinate draws its name from this fact that that in this coordinate system you will have to reach infinite distance to reach actually rho is equal to 2gm. Okay, so therefore uh, eventually you never reach it. Okay, but the advantage of tortoise coordinates is the following, that in the tortoise coordinate the proper time looks like 1 minus 2gm upon rho, not rho star. Okay, but 1 minus 2gm upon rho in times minus dt squared plus d rho star squared plus rho squared, again not rho star, rho squared times j omega squared. Okay, so we seem to be using kind of mixed notation here, but all we have to understand is that the rho written out here is just a function of rho star, and that function is defined up here. Okay, that rho is written in terms of rho star as a complicated function. Okay, so we already see some progress out here, and the progress is the following: that the 1 minus 2gm upon rho is sitting outside this entire object. Okay, and therefore the light cone has fixed angles. Okay, because dt by d rho star is going to be plus or minus 1 all the time. Okay, so therefore if you want to draw a picture in the tortoise coordinates, then you would be drawing 45-degree light cone at every point in t rho star plane. Okay, and that 45-degree light cone has nothing to do with angular uh, coordinates, so therefore it doesn't matter. Okay, fine. Now of course we have paid some price for getting this done, and the price that we have paid is that we have kind of restricted ourselves to a region with rho equals 2gm to rho equals infinity. Rho equals 2gm has been pushed to rho star equals minus infinity, and rho equals plus infinity, of course, corresponds to rho star equals plus infinity. Okay, so this means that the tortoise coordinate covers only the region accessible to the asymptotic observer, namely rho greater than or equal to 2gm. Okay, now in this particular case, no metric component diverges as rho goes uh, to GM, because both uh, GTT and G rho star are all finite. Okay, as rho goes to 2GM. Okay, fine. Now, of course, although they don't diverge, GTT, G rho star do vanish. Okay, and therefore the metric is not invertible at rho equals to GM. Okay, so there's a difference between having a divergent term versus having terms vanishing. Okay, because this is vanishing, we won't be able to invert this metric, but at least the metric is not developing any singularity. Okay, the determinant does vanish. Okay, so what we'll do is that we will kind of uh, make another change of coordinates so that we can kind of make this geometry look a little better. Now, since the light cones are at 45 degrees in this coordinate system, in the tortoise coordinate system, what we'll do is we'll define the light cone variables, which we'll call u tilde and v tilde to be t plus rho star and t minus rho star. Okay, so using that you can write down du tilde is equal to dt plus d rho star, and dv tilde is equal to dt minus d rho star. Okay, so you take these and plug that in back, plug this back into the metric that we had derived some time ago, namely this one. It really affects only minus dt squared plus d rho star squared piece. Okay, and nothing else. Okay, so if you do that, you get a metric which looks like this. 1 minus of 1 minus 2 gm over rho times du tilde dv tilde plus rho squared d omega squared. Okay. Fine. So, what we will try to do is that we will try to use new coordinates which are suitable for describing certain specific behavior of the system. For example, you may be interested in looking at infalling uh, observer's frame, or you may be interested in outgoing observer's frame. Okay, and it is possible to do that by choosing the coordinate system in a specific fashion. So, for example, if you look at v tilde u tilde coordinate system and try to write that uh, matrix in terms of, say, one of the coordinates, say u tilde and rho star. Okay, instead of looking at u tilde v tilde coordinates, which is already written out here. Okay, so if you try to do that, then you know from this definition that v tilde can be written as u tilde minus 2 times rho star. Okay, so that is what is equation. Okay, uh, then you can trade off v tilde and write the metric in terms of u tilde and rho star. Okay, so you can plug that back in and you get an equation which is dv tilde, which is in terms of du tilde times minus 2 times d rho upon 1 minus 2 gm by rho. Okay, right. So if you plug this back in here, okay, we get everything written in terms of u tilde and rho. Okay, so we have gotten rid of rho star also and replace v tilde by u tilde and rho. Now this is the form of the metric that you would land up with by looking at this expression. It's not very difficult to see why it would look like this. Du tilde will give you du tilde squared times this factor, but the d rho du tilde piece would have 1 minus 2 gm by rho getting cancelled. Okay, and you get a factor of plus 2 times du tilde d rho. Okay, which is what we have. So du tilde squared piece has this piece, but du tilde d rho has only a factor of 2 sitting in front of it. Okay, so this is a metric where for the first time we actually see that rho equals 2 gm is nothing special. Okay, until this point, something or I mean, every coordinate system we always saw something weird happening at rho equals 2 gm. Okay, namely that that metric component would either vanish or would diverge. Okay, which is not such a big problem, but we would also have determinant of the metric ill defined typically. Okay, for example, in the tortoise coordinate or in this coordinate rho equals 2 gm, the determinant would vanish. Okay, but this is a coordinate system which is called ingoing Eddington Finkelstein coordinate system. In this coordinate system, you will find that rho equals 2 gm, this factor vanishes. Okay, so one particular metric component vanishes, but this metric component is not very important. Why? Because when you are trying to determine the determinant of the metric, then the determinant of the metric doesn't involve this term at all. Okay, it always involves du tilde d rho and d omega squared piece. Okay, and nothing special happens to that. In fact, the determinant is constant and finite. Well, uh, if you take a rho to be fixed, then the determinant is constant and finite. Otherwise, it is rho dependent quantity, but nothing special happens at rho equals 2 gm. Okay. Fine. So since nothing special happens, we have for the first time shown that rho is equal to 2 gm is what is called a coordinate singularity. By coordinate singularity, we mean that it is an artifact of choice of coordinate system. Okay. For example, in the ingoing Eddington Finkelstein coordinates, nothing special happens at rho equals 2 gm. Okay. No, there is nothing so special about doing this transformation, writing v tilde is equal to u tilde minus 2 rho star. you could have done it the other way around. Namely, you could have written down u tilde is equal to v tilde plus 2 rho star. Okay. If you do that, then you would have gotten rid of u tilde coordinates and written everything in terms of v tilde and rho star. And then you could have gotten rid of rho star in terms of rho. And then you would have gotten an equation which would have looked very similar, except u tilde replaced by v tilde at both the places, and this plus sign would have turned minus. Okay, barring that, the metric would have looked the same with u tilde and v tilde swapped. Okay, and that coordinate system is usually referred to as outgoing Eddington-Finkelstein coordinate system. Okay. Again, you will see in that coordinate system also nothing special happens at rho equals 2 gm. Okay. So therefore, uh, people would say that if there's an infalling observer, that means an observer who sees the Schwarzschild geometry to be something of this kind, okay, because this is the ingoing coordinate system, then the ingoing observer or infalling observer, okay, would see nothing special happening at rho equals 2 gm, simply because this component would vanish, but everything else is finite. The metric is non-singular, invertible, uh, with constant, not constant, with finite determinant. Okay. Uh, so to make it a little more dramatic, one would say that you know that our universe could be crossing the horizon of a supermassive black hole in a multiverse, and we would never know, even if it is happening right now, simply because rho equals 2 gm is absolutely an ordinary point in that geometry. Okay, so infalling observer would never know that he or she has actually crossed the horizon. Okay, fine. So let's try to look at the null directions in this particular case. We are trying to look at radially infalling directions, so d omega squared can be set to 0. Then the null direction would be just set in d tau squared equals 0, which kind of follows from this equation. Okay, so this would tell you that you have 1 minus 1 minus 2 gm by rho times du tilde by d rho whole square plus 2 times du tilde by d rho is equal to 0. Fine. So this equation has one trivial solution, which is du tilde by d rho equals 0. Okay. That tells you that uh, that u tilde is a coordinate which is independent of rho. So it's kind of constant coordinate. Okay. And so therefore, you could say that like one of the light cone direction is du tilde by d rho equals 0. Okay. So if you are trying to draw it in u tilde rho plane, this du tilde by d rho equals 0 is a statement that u tilde is constant with respect to rho, and therefore it should be a horizontal line. Okay, constant u tilde irrespective of rho value. Okay. So what we find is that like one of the coordinates, one of the light cone directions is always horizontal. Okay. Now let's look at the second solution. Second solution would tell you that minus 1 minus 2 gm upon rho times du tilde by d rho plus 1, or rather plus 2, is equal to 0. Okay. So you can solve this equation by rather rearrange this equation to write down du tilde by d rho is equal to 2 upon 1 minus 2 gm upon rho. Okay. Fine. So now, if you are looking at these light cones defined by these two equations at uh, rho greater than 2 gm, then you typically find that the light cone would look like this. Okay. As a result, infalling light would kind of follow this trajectory, and this trajectory is a statement that du tilde by d rho is equal to 0. Okay, so that is the infalling light ray. On the other hand, a light ray which would go along this line, okay, that light ray is the light ray which is outgoing, because this is the angle larger than 90 degrees, and therefore this uh, is a outgoing light ray, and that direction is picked up by du tilde by d rho is equal to 2 upon 1 minus 2 gm by rho. Okay, fine. So, so you can try to kind of track this behavior for different values of rho. Okay, and you will find that when rho is equal to 2 gm, the du tilde by d rho would become infinity. Okay, well, infinity means nothing really. It just tells you that the light cone is going to be vertical there. So one light cone direction is vertical and one light cone direction is horizontal. Okay, fine. So infalling direction is always preserved. Okay, it is the outgoing direction which keeps changing. Okay, but without worrying this, if you kind of continue and go to rho less than 2 gm, then you actually find that your light cone is kind of oriented in this particular fashion. It tells you that the so-called outgoing light cone direction, okay, doesn't exist for rho less than 2 gm. Okay, so not only the u tilde equals constant direction is infalling, but u tilde du tilde by d rho is equal to 2 upon 1 minus 2 gm upon rho is also infalling for rho less than 2 gm. Okay, and that is one of the reasons why it is called the ingoing Eddington single stand coordinate system. Okay, fine. If you try to do the same stuff with V tilde, you will see that the light cones will be arranged differently. The light cones would close this way, and it would actually encourage the particle to go out from the rho equals to gm. Okay, and that is the reason why it's called outgoing Eddington single stand coordinate system. Okay, so although this geometry is obtained by manipulating the tortoise coordinate system itself, because nothing special happens at rho equals to gm, in this geometry could be generalized all the way to rho equals 0. Okay, now this picture that I have drawn is kind of explained in words further down. So that for rho equals to gm, there is this time-like geodesic which can escape to infinity. A time-like geodesic is a geodesic which is sitting inside this light cone. Okay, but if it escapes to infinity, then it actually stays away from rho is equal to gm. Okay, fine. And as I said that for rho less than 2 gm, there is no way of any geodesic, any time-like or null geodesic to ever escape uh, to rho equals infinity, escape to infinity. Okay, of course, space-like geodesic would, but our interest is in only time-like and null geodesics. Okay, rho equals 2 gm is of course a null surface, something we have seen already. Okay, the other aspect of the geometry was that for rho less than 2 gm, t and rho would exchange the role, and rho becomes time coordinate, and therefore a quantity which is uh, ingoing uh, with respect to rho, okay, would actually eventually hit the singularity at rho equals 0. Okay, so So what we have seen so far is that the coordinate system rho and t covers the space rho greater than or equal to 2 gm. But if you go to Eddington-Finkelstein type coordinate system, then we would be able to the uh, cover the space all the way to rho equals 0. Okay. So Uh, so in the U tilde and rho coordinate system, we can kind of look at all the future directed paths, okay, which would cross rho equals 2 gm. Okay, fine. Now, as I said, that we could have, instead of using U tilde and rho coordinate system, we could have used V tilde and rho coordinate system. Okay, and we can construct a new metric, which, as I told you earlier, would be the metric which would look pretty much like the U tilde rho coordinate system, except +2 would become -2 when you swap U tilde with V tilde. Okay, which is what's called the outgoing Eddington-Finkelstein coordinate system. Okay. Uh, there's a way of saying this, that you should have a uh, formulation in these coordinate system for a time independent metric, simply because in the time independent metric you cannot just say that you have only future directed paths. You should also have paths which are past directed, simply because you have time independent metric, and therefore time reversal uh, t going to minus t is the symmetry of the solution. Okay. So one should be able to do the same exercise here. If you try to look at the null directions, then this equation is essentially the same equation, except +2 goes to -2 here, and dv tilde by d rho equals 0 continues to be a solution. Okay, and the other solution is dv tilde by d rho is equal to -2 times 1 -2 gm by rho. Okay, if you try to draw these things, then you will find that dv tilde by d rho equals 0 is a horizontal line. So one of the light cone direction is just a horizontal line, and the other light cone direction is the one which keeps changing its orientation. And you can see that the future directed trajectories in this case are uh, oriented in a direction in which the value of rho would increase. Okay, so uh, so this is opposite of what we see here, where all future directed paths are going from rho equals 2 gm to rho less than 2 gm, whereas here all future directed paths go from rho equals rho less than 2 gm to rho less than 2 gm. Okay, fine. Okay, so the reason why we are interested in geometries of these kind are clearly because we want to ask what happens to the geometry, what happens if you have an infalling observer, or what happens if this point mass emits something uh, out to infinity. Okay, uh, so of course in classical geometry we have just learned that uh, that in this particular case, because rho is equal to 2 gm is a light-like direction, the light wouldn't escape uh, from from rho equals rho less than 2 gm to rho greater than 2 gm, and that is one of the reasons why we would call this geometry black hole geometry. But quantum mechanically, black body could still radiate. Okay, and that is one of the phenomena called Hawking radiation, and which would allow a quantum black hole, not the classical, but the quantum black hole, to radiate uh, its energy, and may it may eventually decay into ordinary geometry, okay, which is what is called a black hole evaporation. And to study problems of those kind, you need to look at geometry. You need to look at the metric written in terms of ingoing and outgoing in terms of coordinates. Okay. Now, of course, uh, Schwarzschild metric is only one particular solution corresponding to a point mass carrying no other additional um, uh, additional quantum numbers, like uh, it doesn't carry any charge or doesn't carry any angular momentum and stuff like that. But if you mm, look at geometries generated by objects which carry more quantum numbers besides, okay, quantum numbers is a kind of bad thing for a classical geometry, but more conserved quantities besides its mass, then you get more intricate solutions, like for example, if a point particle also has a charge, you get a solution which is called Reissner-Nordstrom black hole solution. Even in those kind of geometries, one should be able to write down Eddington-Finkelstein type of ingoing and outgoing coordinates. Okay. Okay. So yeah. So coming back to these coordinate system, uh, suppose you look at the u tilde rho coordinate system, then we can keep u tilde constant and reduce rho. Okay, so that is this geometry that you can keep u tilde constant. That means this horizontal line, and but reduce rho. Okay, as the time ticks forward. Okay, so so that's the statement. Okay, that if you increase time, okay, of the original coordinate system, you can reduce rho by holding u tilde constant. Okay. On the other hand, if you are in the v tilde coordinate system, then you can hold v tilde constant. That means you are on this horizontal line and reduce rho only if you go backwards in time. Okay. So, okay, simply because your light cone is facing this way, time direction is going up in this direction. So therefore, if you want to reduce rho, okay, you have to reduce time, okay, in the original coordinate system. Okay, so now what we have done so far is basically just look at the light cones, okay, and looking at light cones and of course time light directions. That means checking what is the time-like interior of the light cones. We have basically studied only time-like geodesics and light-like geodesics. Okay, or null geodesics, as we would call them. Okay, uh, what we will do now is to look at space-like geodesics, and those space-like geodesics would allow us to kind of further extend this geometry from whatever we have extended so far. Okay. Now, you may think that rho equals 0 was already accessible in Schwarzschild coordinate system. But that's not quite true actually, because Schwarzschild coordinate system, although you would have written rho taking value from 0 to infinity, the metric made sense only between rho greater than 2 gm all the way to infinity. Okay, and that is the reason why we kind of found the tortoise coordinate to be a suitable description with constant light poles. Okay, fine. So that's why Eddington Finkelstein is actually a first genuine extension of the Schwarzschild geometry beyond rho equals 2 gm for values of rho smaller than 2 gm. Okay, so so let's try to kind of see how we can further generalize the geometry that we already have. Okay. Now, Eddington Finkelstein coordinate system was initially written in terms of u tilde and v tilde. Okay, and it was, I'm just writing it in a regular symmetric form by putting a factor of half, writing du tilde dv tilde plus dv tilde du tilde. There's nothing to gain there. Okay, and and in this coordinate system, of course, uh, rho equals to gm is still infinitely far away, simply because this coefficient would just vanish. Okay, so what we will do is we can bring that quantity at finite distance by doing an exponential map. Okay, so let's first define u prime to be e to the u tilde upon 4gm, and v prime is equal to e to the minus v tilde upon 4gm. Okay, so if you do that, uh, now I am writing this 4gm by hand, but it is not necessary to do it that way. You could just define u prime is equal to e to the u tilde upon some uh, quantity, say u0, and determine that by doing this manipulation that we will do soon. Okay, it will tell you that u0 needs to be a constant written in terms of g and m. Okay, fine. So so what we'll do is that, like, we'll bring it back to the original coordinate system, which is rho and t. We know what is u tilde written in terms of rho and t, and so we have to kind of do a few steps actually. So let me just go back and remember u tilde is written in terms of rho star really to start with. Okay, so okay, so like this, and rho star is written in terms of rho, which is rho times rho plus 2gm upon log. Okay, so what we need to do is basically go back to rho and t coordinate system. U tilde would have a factor which is t plus rho piece, which is sitting around here, and then there is a piece which is 2gm times log of something. Okay, some rho upon 2gm minus some kind of stuff. So, but then you have e to the log. Okay, and that brings this factor down here. Okay, so uh, the power half comes because uh, there's a 2gm versus 4gm, so therefore there's a e to the half log, which gives you a square root power out here. Okay, same manipulation for v tilde, you get a square root, and but rho minus t in this particular case. Okay, fine. Given this definition, you can write down du prime and dv prime in terms of du tilde and dv tilde in this particular form. Okay, and just plug it back in. Okay, once you plug it back in, then you can see that you can kind of manipulate the factors uh, because you really need du tilde and dv tilde only. All these factors go and sit out here. Okay, and that is the reason why you get a u prime times v prime in the denominator for this piece. Okay, good. Once you get u prime v prime in the denominator, you can go back and rewrite them in terms of rho and t coordinates. Okay, and you'll find that u prime v prime factor will get rid of the time dependence, which is just as well our metric was static. Okay, and you get a term which is written in terms of exponential of minus rho upon 2gm. Okay, there is a factor, of course, giving you a gm whole cube piece, which is coming from this u prime v prime factor partly, and there's a g squared m squared piece out here. Okay, and eventually get a metric which takes the form of this type. Okay, now this is yet another form in which you see that rho is equal to 2gm, nothing special happens. Okay, because this entire metric is well behaved. Rho equals 2gm, this just becomes a constant, and nothing special happens at this particular point. Okay, so unlike the Eddington-Finkelstein coordinate system, in which at least some metric component was going to 0, which is of no consequence in the sense that metric was non-singular, but at least some component was vanishing. In this particular coordinate system, even that is not affected. Okay, so we actually end up with a matrix which is completely well behaved at rho equals 2gm. Now, notice one more thing, that, like, you can show that, uh, because there is a du prime dv prime factor multiplied by some overall term. Okay, u prime and v prime are null directions. Okay, and therefore you can write down del u prime and del v prime as the null vectors. Okay, so there's an overall factor sitting around outside, but light cones are at 45 degrees. Okay, good. So there's one more change of coordinate that we could do, and that is a kind of trivial change of coordinate. If you have a metric which is written in terms of u prime v prime, sorry, du prime dv prime, you can always bring it into a form, you know, minus dt squared plus d rho squared kind of form. In this particular case, what we'll do is we'll define u and v to be u prime plus v prime and u prime minus v prime. And if you do that, then your final metric is going to look like some uh, same overall factor uh, sitting around here, which is 32 g cube m cube upon rho times e to the minus rho upon 2 gm times minus dv squared plus du squared plus rho squared d omega squared. Okay, there is nothing that we gain by doing this change of variables, because this metric and this metric are essentially the same. Okay, that is just making a light cone kind of choice. Uh, Whereas UV are kind of usual space and time coordinates. Okay, so this metric that we have written down is called the Kruskal metric. Okay, and UV theta phi are typically referred to as Kruskal coordinates. Okay, in this geometry, it's kind of obvious now that there is an overall factor sitting in front of the null directions, written in terms of space and time coordinates now, this thing, but v is equal to plus or minus u are essentially radial null geodesics. Okay, and uh, and v equals, actually v equals plus or minus u is the event horizon, and v equals plus or minus u plus some constant are the radial null geodesic. Okay, so uh, so among all the possible radial null directions, v is equal to plus or minus u is the horizon, event horizon, which is, as we have seen in various other coordinate system, is a null surface. Okay, fine. Now for a constant rho, remember, like, rho is not an explicit coordinate here. Rho should be kind of interpreted as a function of du dv kind of things. But if you don't like it in this fashion, you can always revert it to rho, given that u and v are written in terms of rho and t here. Okay, so if you ask what are the constant rho surfaces, okay, then you'll find that the constant rho surfaces can be written as u squared minus v squared is equal to rho upon 2 gm minus 1 times is the rho upon 2 gm. So constant rho surface would essentially correspond to setting this quantity equals constant, but that is equal to u squared minus v squared, and therefore it must be in a hyperbola. Okay. On the other hand, if you are looking at constant t surfaces, okay, then constant t surfaces, if you go back to this expression, then constant t surfaces, the t dependence is there in the sine hyperbolic and cos hyperbolic function. Okay, they would correspond to straight lines. Okay, simply because if you take the ratio of u, if you take the ratio v by u, okay, then all these rho dependent pieces would just cancel out, and you get a tan hyperbolic t upon 4 gm. Okay, but that tells you that for constant t, v is equal to some constant times u. Okay, that is the statement. That if you take t constant, then v is equal to some constant value times u, but that is a statement of a straight line. Okay, passing through the origin. Okay, by passing through the origin, because v is equal to some constant times u, but there is no plus additional constant. Okay, so therefore, if u is equal to 0, v is also 0. Okay, and that is the origin. Okay, so here's the geometry and modular quality of my drawing. As you can see that uh, it is kind of tilted by like 10 or 12 degrees or maybe 15 degrees, I don't know. But uh, these are supposed to be the light cone directions. Okay, this is the constant T surface. T equals uh, all these radially outgoing directions are constant T surfaces. Okay, whereas constant rho surfaces are hyperbolic, like that. Okay, rho equals 2gm is of course horizon. Okay, so which are asymptotes to this hyperbolic. Okay, is that a question? Okay, so far what we have been talking about is uh, about mostly about rho equals to gm. Okay, and very rarely about rho equals 0. Okay, but rho equals 0 is a location at which the point mass is sitting. Okay, and in fact what happens if you look at the Schwarzschild metric is that rho equals 0 has a singularity again. Okay, but unlike rho equals 2gm where also we had a singularity which is a coordinate singularity, rho equals 0 is not a coordinate singularity. Okay, so in fact what we can see is that at rho equals 0, some curvature invariance diverge. Okay, as against rho equals 2gm, where nothing special happens. Okay, okay, so I think I'll stop at this point. We'll pick up from here next time. Okay, any questions?